Yeah.
Hi, Abby. How are you doing?
Hi, sir. I'm doing well. How are you?
Very good, very good. So, till now, we have done about the radian measurements. We have also seen how do we sketch trigonometric function graphs, sinusoidal and
Yeah.
tangent, right? Any difficulties so far?
No, I think last lesson when we caught up on everything that I was struggling on, I think now it's all really thorough in my head.
Very good.
It's good.
So, once you know all that, it's very good to see into the real life situations and how do we model these real life situations using trigonometry. That's the
Right.
topic for the
Yeah.
day, right? Are you excited about it?
Yes, I am. I always like a bit of practical element in maths. It's rare, but when it comes, it's good.
As you know, I travel a lot and I shoot videos. That's my hobby, actually. So I'm going to share with you a beautiful place. It's in New Zealand. So
All
let's
right.
go through a video. These are the waves, and we'll see how do we model these waves, right? So we'll work on
Okay.
that kind of a thing today. So let me just share that screen with you. So can you see my video? That's my YouTube channel, and we do have a lot of math videos and, of course, nature videos, right? So this is
Right. Right.
the visit to New Zealand, and a very beautiful place. I think everybody should visit New
Should
Zealand. That's
go.
my feel. You should
Yeah.
go there, right? Very beautiful. So let's watch this. So that is Paparoa National Park in New Zealand.
All right.
And the
Yeah.
waves that
Very
you are
beautiful.
seeing, these waves can be meters high, very high waves.
Oh my God.
The rocks which
It's
you
kind
are
of scary.
seeing, yeah, and the rocks which you're seeing have been carved by these waves over a period of time,
Oh.
billions of years.
Oh, because
And
it's keep like hitting it and then it erodes.
yeah, it erodes.
Oh,
And
right.
if you go further, I mean, you see those blowholes, right? So the waves they go
Yeah.
underneath, and then through the rocks they have formed the blowholes, and they like shoot out. There's
Oh,
these spots
wow.
are on my camera. So they actually these waves come out and they can, you can just feel it. It's so beautiful.
Yeah. Yeah.
So that's
Oh,
an
wow.
amazing
That's
place.
amazing. Yeah.
It's amazing, right? I just move forward and
Yeah.
take you to the other part of it where, I've seen this, I've shot this from different angles. So I like to show you the
All right.
place from, different angles, and then we'll talk about a mathematical problem which can be solved. That's we call blowholes, right? It'll go underneath that rock and it'll shoot from here. You'll see that. It'll shoot from here somewhere. It's nature. You're never sure when something is going to happen. So you got to wait for it.
Yeah. Yeah. It's unpredictable.
Unpredictable. So you got to wait for it. So, when I was taking it, a couple of times I expected it will come out, but it didn't. See now.
It
You see
didn't.
that?
Yeah. Oh, wow.
It's beautiful. Really beautiful. Okay,
It's
so I
good you
think
got it on
we'll,
camera.
yeah, yeah. You see that?
Yeah. That's
Amazing,
a
right?
good shot. That's a good shot.
So these are the blowholes, and then you see that thing coming out.
Yeah.
Amazing. Now, based on this, we have a similar place in Canada also. So my
Oh, right.
question is related to a place in Canada. So
Oh,
let me
okay.
take you
Yeah.
to the question now. So I'll stop sharing this. Now on the screen, what are you looking at?
Modeling with trigonometric functions.
Correct. So that's our topic for the day.
Okay.
So there are many applications which we can model using trigonometric function. Ferris wheel is one of the most common, correct? So every book starts with Ferris wheel. There'll be tons of examples on Ferris wheel. So that picture kind of gives you an idea that, we are looking into modeling using trigonometric functions. It makes sense.
Mhm.
There's a round thing which just rotates, it's periodic. It makes sense. The height is changing. So we can write a function which relates the height of a person on the Ferris wheel with time, correct? So that is how we could
Yeah.
actually model the situation. But the example which I have taken today is related to the video which we shot. So let me go through that example and now also share with you another place which is kind of similar, what you saw in New Zealand. And this is in Nova Scotia, Canada. So I've also given reference of the website here. One can go to those websites and see how beautiful this part of Canada is, the Nova Scotia. Okay, the question which we are really interested in answering today is, let me just highlight it. Example 1, modeling tides. Now, can you read this or it's too small?
Oh no, I can read it. So you can experience the
just
highest tides in the world.
Okay, now I think it's very clear. Yes. Can you please read it
Okay.
again?
Yes. So you can experience the highest tides in the world at Bay of Fundy, Nova Scotia. Scotia, Canada, at the height of the bay in Minas Basin. I don't know what this is, sorry. The height of the tide can reach an incredible 16 meters, or in other words, 53 feet. On one day in March, the tides have a high point of approximately 40 meters at 5 a.m. and a low point of approximately 3 meters at 11 a.m.
Correct.
And then
yeah, so basically the question is that, we are modeling the tides. And this is one world's best place to watch the tides. Actually, I've seen it. They just go high and low. That means, those flower pot which you saw, if you go at high tide time, you will just see only the tip of it, just the vegetation on that rock.
Right.
And if you go at the low tide, you see, the sand and all those animals left behind, like, crabs and all those things left behind. So that's the low tide.
Yeah.
And you can actually walk kilometers towards the sea. So that is the huge difference in the two timings when you watch the tide, right? So again, coming back to this question, it says, at the height of the bay in Minas Basin, the height of the tide can reach an incredible 16 meters. 16 meters is like multi-storied building. You get that 16 meters. On one day in March, the tides have a high point of approximately 14 meters at 5 a.m. and the low point of approximately 3 meters at 11 a.m. Right? So that is one day's work. Right? Now, based on this, we need to write a cosine function to model the situation, plot the graph to show the expected height of the tide for the day, anytime during the day. If you want to know what is the height of the tide, we should be in a position to know. Explain how you can write sine function to represent this situation. So we'll begin with the cosine function and then write the same function as a sine function. As you know, the two functions lag by quarter of the cycle, correct?
Right, yeah.
That is a phase shift, right? So we'll incorporate that quarter of the cycle, phase shift. And then, can you express the situation in two other related sinusoidal functions? So whenever we model, we could actually give easily 4 equations modeling the same situation. 2 in sine, 2 in cosine. Okay, so that's what we are going to learn. And part E is find the duration when the tide was less than 7 meters during the day. So that will help you to see how do we solve a trigonometric equations. It has got all the components of this unit. That's the beauty of this question. Do you understand that?
Yeah.
Correct. Now, tell me, how are you going to solve this kind of a question? What is going to be your approach? Let's discuss that. So what I've done here, I just copied the question here so that we could discuss our approach here, right? So yes, can you tell me how will you approach this particular situation to model?
So, um, would you have to use the different heights at the different times as kind of like maybe coordinate points or?
Very good. So that is what is required. So we have these two high and low points. So basically,
Okay.
as we do is, we basically begin with a sine wave as a or a cosine wave, anything you may call one and the same thing.
Yeah.
So we begin with the axis, and that axis is the axis for the wave, and then we have a maximum and a minimum, correct?
So 14 and 3.
Yes, 14 and 3. So do you see that I'm not drawing the y-axis? I don't know where exactly the
Yeah.
y-axis should be placed. So I do a
Yeah.
general graph, correct? So I just say, well, if it is a cosine function I have to model, I'm always looking at the maximum first, right? It starts with the maximum, correct? And then it
Yeah.
will go to the average point, then it'll come to the minimum, then go to the maximum, average point, middle point, and then the max, right? So that becomes the cosine wave for us, correct?
Yeah.
If I have to really, I could actually connect these points and make a wave. Or what I do is first I draw a wave and then put the points. So I can do either way. So what I do normally is something like this. So I'm just telling you from my experience how practically we do it. So we just draw a wave.
Yeah.
I prefer to draw a sine wave. It may be whatever, right? So I prefer to go with the sine wave. I like this graph. That is my wave, correct? Now we need to model the cosine function, and therefore what I'm saying here is that, well, that's my point, which is y equals to 14, right? 14 meters is the height, and this is my minimum,
Yeah.
and this is at y
3.
equals to 3 meters. So clearly the center point is what? So this is, and the type of model means I'm looking at this equation. I'm looking at the equation which is y equals to a sine k x minus phase shift plus q, which is translation up and down, correct?
Yeah.
Q is this middle line, right? So the average mean Q. So this is equal to maximum plus minimum.
Divide by 2.
Yes. So in this case, it is 14 plus 3 divided by 2, 17 divided by 2 is what?
8.5.
8.5. So we got the value of Q, correct?
Mm-hmm. Yeah.
Now, second thing, A. Capital A is what? Capital A is this distance. Distance from the mean, the average, to maximum or minimum. So we could do 14 minus, let me write down here, 14 minus 8.8, right? 8.5.
8.5.
Yeah.
5.5.
So we got the value of A, which is 5.5, correct. Now we have to look for K, the time period, right? So time period, we are given two times here. One is at this point, when is the maximum and when is the minimum, correct? So these are the two times which we are given. The first time is 5 a.m., correct?
Yeah.
The second one is at 11 a.m. Now, this is only half the cycle. The full cycle is right here. Do you see that?
Yeah.
If you look at maximum and minimum, we are only looking at half the cycle. So half the cycle is how many
6
hours?
hours. 6 hours.
So time period T is basically 2 times 6, right? That is the full cycle, right? So it'll be 12 hours. And normally, when we are, modeling real life situation during the day, and if you want that to repeat every day, that means the cycle should be 12 hours or 24 hours, something like this, correct? Otherwise, we cannot really model. So we approximate as per the season. It changes with the season, right?
Right.
Yeah, sunrise will be at 6 right in the middle of the summer, but then it could be something else during the season, correct?
Yeah.
Winter it will be late, right? Maybe.
Yeah.
Okay. So now we know the value of T, and therefore we know the value of K. If you're working in radians, which we should be working at this stage, 2 pi divided by T, right? Which is 12. Or pi by 6 is the K value, correct? So we know what is K. K is 2 pi or 360 divided by the time period. Since we found that the time period is 12 hours, we just divided 2 pi by 12 and we got the value of k, correct?
Yeah.
The last thing, which is one of the most difficult thing to calculate, is the phase shift. How do I calculate the phase shift? Now look at it. We are actually designing to find out cos function, right? We actually want the cos function in the question. Sine is another part of it. So we want phase shift for the cosine function, correct? Cos. Cos starts with maximum. So if it is starting with maximum at t equals to 0, then there is no phase shift. However, it has a maximum at 5 a.m., correct?
Yeah.
So how much was the phase shift?
5.
5, correct. So we'll start at t equals to 0 when time starts when it is 12 midnight. Do you see that?
Yeah. Yeah.
That means clearly the value of p is 5. Is that clear to you?
Oh.
So we
Yeah.
got our cosine function. Perfect.
Yeah, that's really clear.
We have all the components here. Clearly you can see how in this chaos we have the complete solution.
Yeah, yeah. So this is how you model with using trig functions.
Where is
because all the values are in the question.
Correct.
Oh, right. Okay.
Correct. And if you want, now we write down the equation, which is what? Which is y equals to the amplitude of 5.5 cos of, well, how much it was?
8.5? Oh.
8.5 is the middle value, right? 5.5, right? Maximum minus this, right?
Yeah.
14 minus 8.5.
Pi over 6. All right, yeah.
Cos of
pi over 6.
Pi by 6, correct.
X minus 5.
Plus 8.5.
Plus 8.5, yeah.
Simple, correct?
Oh.
Do you understand?
Yeah, very clear.
So that is how we model tides or anything else. Now, another part of this question was, how do I write this as a sine function, correct?
Yeah.
Now, sine function and cosine function are related by quarter of the cycle. Do you see? We are actually now looking for this point. When was this point? Because it starts rising. Do you see that? How much before this point? You get this? This point is at, see, if you look at it, this is half the cycle, right? This and that one is quarter of the cycle. Right?
Yeah.
So that means quarter of pi by 6, right? So what is quarter of pi by 6?
Pi over 24.
Correct. So pi by 24, if I shift left, I mean, then I get the sine wave. You get the idea?
Oh,
so I get the sine wave. Doesn't make sense.
Right. So so whenever you want to find sine from the cos graph, you just need to do a quarter of that time period.
Yes. So is this concept clear? Let me take you now through the actual typed in neat and clean solutions so that we can see what we really did, right? Do you see that? Okay. So can you please read the cosine function model which I have written here?
Yeah. So we will assume that the height in meters is a periodic function of time in hours. So consider t equals 0 at midnight, 12 o'clock, and the time in hours along the x-axis. So maximum height, m equals 14. Minimum height, m equals 3. Axes, it's m, the capital M plus the small m divided by 2, which we got as 8.5.
Okay.
And then the amplitude is capital M minus the m, so 14 minus 3, and then divide by 2, you get 5.
Okay.
And then to get the time, you look at the high tide, so that would be 5 hours.
That is given. Yeah.
Given in the question. So you know the time period. So half of the cycle is during the time difference between the time for high and low tides. The period will be twice this value. So you do the difference and then multiply it by 2 to get the time period.
Correct. Now
then, looking at phase shift. So trying to find the value of k. So we know we have to do 2 pi divided by the time period, and we've got the time period as 12. So 2 pi divided by 12 is pi over 6. And then we are given that the maximum at 5, so cosine function will have a phase difference of p of 5, and you can model this by this situation.
Correct.
And then the cosine function to model the situation is, and then we just subbed in all the values.
Perfect. So that is how you do it, right? So what I did is I just actually sketched the graph also exactly given to us. So here you can see the maximum, which occurs at 5 a.m. in the morning, and the minimum occurs at 11, correct?
Yeah.
That becomes your sine function. So, I mean, the cosine function, whatever you may call, right? So that is a situation, real life situation given to us. So once you have this, doing all those calculations, knowing maximum, minimum, finding the average, amplitude, then the phase shift gives you the cosine function. Cosine function means we're looking into this phase shift of 5. But for sine, the phase shift is only 2. How did we get that? Because we moved it pi over 24 left. You get the idea. To get this particular phase shift when we were writing in terms of sine. And you can very clearly see the sine function actually starts here. So that is how we get the sine function, correct? So we'll go through this calculation also of how do we calculate the sine function, right? So yes, Amy, once you take the notes, you can start reading from here.
Okay, so equivalent sine function for h of t equals 5.5 cos pi over 6 t minus 5 brackets plus 8.5.
Correct.
So since the wave starts a quarter of the cycle before the cosine wave, so in other words, the sine leads the cosine function by a quarter of a cycle. So here the time period is 12 and its quarter will be 12 over 4 or 3. Simplified. So h of t equals 5.5 sine pi over 6 t minus 5 plus 12 over 4 and then plus 8.5. So you just sub that in and then we simplified it to t minus 2 in the brackets.
Because it was earlier by quarter of the cycle, the time period is 12 hours, quarter of the 12 is 3. And because it was earlier, we added 3 to t minus 5, and that gives us t minus 2 in sine wave. You see that? Right. So you can check this value that on the graph also, this is at 2, correct? So this is t, correct? Is it okay?
Yeah.
So that is how you could model this in sine. Now the question is, how do you get 4 equations? So we got 2, right? One for cosine, one for sine. So the second equation is, I could start from this place and then go up. That is also a sine function, correct?
Right. So any point can be the origin. Yeah.
I could go back and take a point from the top, or I can even take this point to write the cosine function.
Yeah.
So instead of saying my phase shift is 5, I could say my phase shift is 17. Do you see that? 5 plus 12.
Yeah.
5 plus 12. Again, it's the same wave.
Right.
I could get infinite solution, not even 4. You get the idea.
Yeah.
You're only adding that period on top of it and getting the whole thing, correct?
Yeah.
So the phase shift P plus we add the time period, let me call this time period as capital T, to get multiple solutions once we get a sine equation and a cosine equation. Is that
right? But if there was a restriction, you can't have as many, like maybe just 3 or 4 graphs.
If the restriction was between, let's say you are visiting the place in the afternoon, let's say, right?
Yeah.
So you want to go for the high tide after 12, let us say, right? Yeah. So then you will look into that particular day, correct?
Oh, right.
Now,
okay.
To give you more information on this, if you visit Bay of Fundy, for example, it's a national park, if you visit that place, they will actually give you the calendar of and plus the timings of the tides for the day, hour by hour.
Oh,
yes.
Okay.
They will say this will be the level, correct?
Yeah.
So this is important because you want to see the different phases of this particular tide. You may like to even venture into the sea when it is a low tide, right?
Yeah.
Because low tide is not very interesting. High tide is kind of dangerous. So low tide, you can go canoe
you can
and
get swept away. Yeah. Right? So it's good to know the timings.
Timings are very important. Even some people do a lot of collection of shells and whatever. Low tide may be a good time for that. High tide is a good time to watch the sea. I mean, it's like amazing,
Yeah.
splashing all over the place, right?
Yeah. I want to be there now.
Yes, yes.
Yeah.
So in this part, we have actually understood modeling. Is that clear to you?
Yeah, very clear.
Now, second part is how do we solve trigonometric equations, correct? So I'll just move forward and extend this question. Can you please read this part? Just the question.
Yeah. So duration for the tide below 7 meters during that day.
Correct. So what we will do now is we'll work on this. Now what we will do is we'll figure out, we know this tide, right? Let's go back to this. So we want to find when is it below 7 meters, right? We know minimum 5, which is too low for us. Maximum is whatever, very high for us. But 7 seems to be okay. So let's say 5, 6, and 7. So we are looking for this line, correct? Let's say we are visiting the part, and well, it figures out that this is a nice time to go. Safe also, because at this time it is going further down, not coming up. So we are safe at this time. So let us say around before 8, maybe a good time to go for a boating, right? Or, canoeing in this particular, right? So that we got there, kayaking, whatever you may say, right? So we want to figure out what could be those times, right? In the morning, in the afternoon, whatever, right? So during the whole day, correct? So how do we figure this out? Basically, we are saying that whatever equation we have, we'll equate it to 7, correct? And find the points of intersection.
Yeah.
That is what we have to do. So that is solving trigonometric equation. Is that clear to you?
So do you draw the line of y equals 7?
We can draw and do graphically, but we'll do algebraically to get very accurate result, correct? So you have recorded this equation. We'll work with the cosine function. Just copy. You have this equation, right?
In my book?
No, you just took, Then we'll try to solve the equation on a fresh page, okay?
Wait, can I just quickly write that down?
Yeah. Right down. 5.5 cos pi by 6 t minus 5 within brackets plus 8.
Got it.
Good. So we'll solve this particular question. Okay, we did this, right? Okay, so this is what duration, right? This is what we are going to solve. Correct. So we have our equation and we want 7 meters. So instead of y, I'm writing 7, correct? Amplitude was 5.5 cos of
pi over 6 bracket
t
minus 5
plus 8
bracket plus 8.5.
Now that is the equation which we need to solve, correct? We know there are a couple of points, right? So let me just draw this graph on the side. It gives you a fairly good idea of what we are trying to figure out, right? So let's say these points, correct? We want those points. We're starting here, correct? This was 5 for us, correct? Okay. Now, so what we will do here is we'll solve by bringing 8.5 to that side. So 7 minus 8.5, correct, equals to 5.5 cos of all this, correct?
Yeah.
And then that is how much? 7 minus
1.5
divided by 5.5 equals to cos of pi by 6 times t minus 5. Clear? Now, now look here. When we say cos is negative, it means what? It means we are working in quadrant 2 or 3, correct?
Yeah.
So that is how you're going to solve it. That means we are working in these 2 quadrants, right? So I'll find this angle and I have to find that angle. So those are the 2 points which I may find. Do you see that? Can you correlate these 2 points? Right?
I can, yeah.
What we will do to find this point is basically we'll find related acute angle alpha. So we call this as related acute angle alpha.
Okay.
Normally books use beta. I don't know why, but I use alpha. Acute angle alpha. Okay. Books use beta. Okay.
It's easier to draw.
Yeah. I like alpha. Okay. It comes with A. So for that, I will not use negative value because we are in quadrant 1. So we'll get a positive value.
Yeah.
From 180, we can add and subtract to get both the values. You get the idea.
Yeah.
So we'll do cos inverse of this factor, which is 1.5 over 5.5, whatever it comes to. Can you tell me how much angle you get in radians? You have to move your, check this in radians.
Okay.
Yeah.
So cos minus 1 of 3 over 11.
Yeah, cos inverse of. What do you get?
Yeah. 1.2945.
Okay. So that is this angle alpha. You get the idea? So
yeah.
Actual angle will be what? That means, what is this
180.
equal? 180 plus and 180 minus. You got it.
Yeah.
Perfect, perfect. That is what we were up to. So now we know 180, no, but we'll say pi because we're working in radians, right? Pi plus 1.2945 is equal to pi by 6 times t minus 5, correct? This becomes one equation. And the other equation is pi minus 1.2945 equals to pi by 6 times t minus 5. You get the idea. So those two equations will give you these two angles, theta 1 and theta 2. Do you see that?
Oh, right. Yes. Yeah. So it's very important to find the related acute angle. Yeah.
If you use calculator directly to find this angle, calculator might give you that angle. Do you see that? It may not be of any use to you. I'm not sure what will it give, but you know that it may give. Sometimes it gives you the first angle. Sometimes it gives you theta 1 also. But the idea is to get the related acute angle and then any other angle.
Gotcha. Yeah. Yeah.
So now you can use a calculator. That means you have to just multiply this by, I mean, you do this math and then find out the value, correct? So you'll get two answers, and those will be the times when the tide will be at 5, at 7, right? And if the question says below 7, that means we are looking into this interval, correct? We are looking into this interval in time between these two. So that will be our solution.
So do you just find the two times and then subtract?
You're not really. We'll say from this to that.
Oh, okay.
Yeah. If they say duration, then you subtract and say so many hours.
Oh, so that's the wording. Okay, got it. Yeah.
Words are very important, right?
Yeah,
so,
yeah.
Okay, so let's go straight to the solution, which we have already done. The important thing is you understood the concept, correct?
Yeah.
So, okay. So can you please, read the solution?
Okay. So from there, okay. So we will solve the equation for h of t, which equals 7. So all we did was literally place 7 where h of t is. Then we moved the 8.5, so 7 minus 8.5, and then divided by 5.5. So we have minus 3 over 11 equals cos of pi t minus 5. And then because the cos value is minus 3 over 11, it's a negative in a it has to be in quadrant 2 or 3 because it's negative, using the cast rule or whatever rule that you have. And then what you have to do is find the related acute angle, because like Sir just said, if you just sub it right in the calculator with the negative, it could give the other angle going clockwise, which we don't want. So just find the acute angle, and then all you need to do is do 180 minus that related acute angle and then 180 plus that angle. Oh, but no, because we're working in radians, sorry, we're using pi.
Right.
And then, so then you've got your values, and then because you used have the equation pi plus the 1.29457, which equals to the pi over 6 t minus 5, and then you do the same thing for the pi minus the 1.29.
Right.
And like that, you get your two values.
Right. So simple equation is, when you're using the calculator, we have pi minus 1.294 multiply by 6 over pi, correct? The whole thing. And then you add 5, correct?
Yeah.
So straight away you get the value of t.
Yeah.
From the other side, you have to just use plus here and get the second value of time, right? So at those times, we are working on a time from 1 to 24 hours, correct? So at 13 hours, 13.48, you can convert 0.48 into minutes to give your answers in hours and minutes. Is that clear to you? So 0.48 will get to multiply by 60 will give you 29 minutes, right? So this time will be now converted. So we have the time which is 8.53. This is in hours, right? So let's write capital H. And 13.48 in hours, correct? So you can convert this. And what you get is 8 hours. And the first case is 32 minutes. And the second case is 13 hours, 29 minutes.
Yeah.
Is that clear to you? So we get the exact time when the tide will be at 7 meters. Since we need the interval, we will say, well, the interval is between these two times. Is that clear to you?
8.53.
8.53. Let's get back.
And 13.48.
Okay, we got these two times, right? 8.53 and 13.43. Okay. So what we have to do is we have to find the middle value. So once I get that portion has not been done. So for answering this question, I could have said that between 8.32 to 13:29. It is below 7 meters. Is that clear to you?
Yeah.
So that is below 7 meters, correct. So we got this portion, right? How do we get the other values? That was our second question, right? How did I get one? I'll tell you, explain you that. So, or you can do time period is of 12, right? So you can just minus 12. You do minus 12 from here, go back, and minus 12 from here. So if you minus 12, you get 129. So you get this point 129.
So 13.48 minus 12.
Yeah. That point. 1.29.
Yeah, I got that.
And the other point which we are not looking at will be corresponding to this, minus 12.
Wait, where did the 12 come again? Sorry.
12 is the time period. It will repeat after every 12, right?
Oh,
For
right.
example, if you have to go from here to this point, you'll have to add 12, correct?
Yeah.
Because periodic.
Oh, so did you get that from looking at the graph?
Yeah. Straight away you can go. So you don't even have to go with the center and all. You can go like this also.
Yeah. 2 ways,
so just add 12 because we calculated these two times were these times, correct?
Mm-hmm. So to find the next one, you just add 12 to both values.
Yeah, because we were working
we
were working in this domain. So we found the next points where it was 7. Right. During that domain, we know it is below this. But if you want to know early on when it was, correct, you could be, right?
Yeah.
Or the next day when it will be, you can add 12. Keep on adding 12 to these 2 points. To these 2 points. Is that clear to you?
Yeah. And then convert to hours and minutes.
Yeah, duration. So the duration will be, let's write like this, will be this, or it could be add 12 to this. So next day. If you add 12 to this, you get next day, right? 12 to this.
Yeah.
So you'll be 2032 and 12 to this. 25, 29. You get the point, right? Which will give you effectively next day this portion.
Yeah.
Which is this portion here shown. You see that portion?
So the next time it comes below the axis.
Yeah. Next.
No, below the 7 meters. Sorry. Yeah.
You get the idea?
Yeah, very clear.
So you can
get looking at the time period.
Previous or preceding or following with by adding 12 to whatever you got in between. Doesn't make sense.
Right. Yeah.
So that is how we could get our, because the question could be next day, what will be the best time? Let us say you are late today, right? Then what to do?
Yeah. So you have to calculate.
Very practical things, which you see when you visit these parks, you understand the importance of all these calculations.
Right.
Does it make sense to you?
Yeah, very clear.
So that was it. We can summarize today's lesson. Like, what did you learn and how was it?
Yeah, so it was really good. I definitely enjoyed the videos of the waves, and just seeing it in the practical element, like with all your questions that you've shown. It was yeah, very good. Yeah, I just wrote a couple of things down in terms of when we were solving the trigonometric equations algebraically. But it's important to have the graph alongside, because as we saw when we calculated our two values, only by looking at the graph we could realize the time period, because we were just given the equation. But you can calculate the time period just looking at that equation, as we learned from 2 pi divided by the time period. But it's just nicer to see. So yeah, then we calculated all of that, and we also used our previous knowledge of all the cast rule, the related acute angles, to find the two values. And yeah, like you said, sir, because this modeling is quite a practical real life scenario, so to see that done with maths is quite, yeah, really impressive.
Yeah. The project which we give in trigonometry is that you design your own roller coaster using different functions, right? Yeah, because roller coasters could have all kinds of rides, right? So design your own roller. You could use exponential, logarithmic functions, parabolic, polynomial equations, and trigonometric functions to get to that roller coaster ride. So that becomes a very interesting assignment based on our learning so far. Okay.
Yeah, definitely.
Right. So I'll recommend that you continue with your questions from your book. Try to understand how do we, if you have any questions, we'll solve them in the next class. Or
perfect. Thank you so much, sir. Yeah.
Okay then.
I'll be helpful. I really appreciate it. Bye, sir. Have a good one.
You too. Thank
Bye.
you.